Hello everyone, my name is Ngoc Tram. I am a postdoc at Max Planck Institute for Radio Astronomy in Bonn, Germany. Today I would like to present you the probing dust grain alignment mechanism in galaxy and then show you the case of study of M51. This presentation is on behalf of Professor Tim Hong in Kasi, Korea, and Dr. Enrique Lopez Rodriguez at Stanford University, USA. Dust polarization allows us to probe the magnetic field. If somehow the grain can align with the magnetic field along the minor axis, the absorption will polarize along the magnetic field. Therefore, the polarization vector will directly probe the position of sky of the field. This absorption polarization is observable at the short wavelength from UV to near infrared. On the other hand, the dust grain will re-emit, and this re-emission will polarize perpendicular to the ambient magnetic field. Therefore, rotating the polarization vector by 90 degrees will help us to trace the position of sky of the field. This emission polarization is observable at longer wavelength from 5 infrared to sub-millimeter. This mechanism is are widely used to probe the magnetic field from the interstellar medium to extragalactic scale. How about the observational properties? First, for the absorption polarization, on the y-axis, show you the polarization degree as a function of inverse wavelength in the y-axis. Observation show in the dot, in the circle, and overlay with the extinction curve. What we can see from the figure, the absorption polarization degree gets decreased towards shorter wavelength, let's say UV optical, but the extinction is high at these wavelengths. Therefore, the small grains are quickly aligned. Here, the polarization fraction of the thermal dust emission as the function of the wavelength measured toward 2 cloud in OMC. What we can see the figure, the emission polarization degree gets increased toward higher wavelength. Therefore, the large grains are effectively aligned. So the successful theory describing dust grain alignment should successfully reproduce those observational properties. Here I go through the development of the theory of the alignment theory. In 1951, David Cranston proposed dust grain can be aligned with the can be aligned through the paramagnetic relaxation. Instead, the grain are spun up by cross collision, and then the dust grain will align with the magnetic field. But the rotating of large grains is effectively damped by the collision itself. So the large grains are quickly aligned, which is opposite to observation. And then in 1979, Purcell proposed that dust grain could be superthermally rotated due to the recoil of the formation of molecular hydrogen from the grain surface to the gas phase. This suprathermal rotation will have to overcome the damping. Then the dust grain can be aligned with the magnetic field through the paramagnetic relaxation. But this talks fixed the grain body. So the alignment is reduced by the thermal flipping as demonstrated by Lazarian and Grain in 1999. So it's not able to align large grain either. In 1976, Loginov and Mitrofanov proposed that dust grain can be spun up by scattering of photons on a grain surface. And then Lazarian and Thiem demonstrate that this talk is able to align large grains, which is very good. 1952, wrote alternatively proposed that grains are spun up by stochastic gas collision. It's called a gold alignment. But in 2019, Thiem and me demonstrated that this talk is not efficient to align large grains. Finally, Lazarian and Thiem proposed that grains are also spun up by the regular torques due to the gas collision, which is called the mechanical torque. This torque is demonstrated to be more effective than the gold alignment above, and also effectively align grains with either sub or supersonic incident gas flows. Even though the relative importance between radiative torques and mechanical torques has are not been studied yet, but the radiative torques are expected to dominate over the mechanical torques in most astrophysical conditions. So please see the very nice review by Lazarian and team 2021. And how the radiative torque alignment works. First, the dust grain could be magnetized through spinning. If the dust grain stay at rest, the net magnetic moment J is 0, but the spinning dust grain acquires net magnetic moment J. And then the magnetic moment J will couple with the magnetic field through the Lamer precision. So dust grain align with the magnetic field. Here is a sketch of the rad alignment theory. We have the magnetic field here, the radiation light beam this direction. We have grain, and so grain will spin up by the radiative torques, and then the magnetic moment will align with couple with the magnetic field. So grain align with the magnetic field. There are some parameters within the rad alignment theory. One of those is the angle between the magnetic field and the radiation direction. Heron 2021 calculate the total alignment degree as the function of this angle for different grain size, show different colors with no magnetic field and using the standard radiation field. So for the standard radiation field in ISM and no magnetic inclusion inside grains, the total degree of rad alignment can reach up to 50%, which is sufficient to explain observations, which is very good. But please note that if the magnetic inclusion is taken into account, the degree will be higher. So if the grains align with the magnetic field, we call that the P-rad. And the time scale of this alignment is characterized through the Lamer procession, which depends on the grain size, the magnetic susceptibility, and the magnetic field. But grains also be aligned with the radiation field. In this case, we call the KRAS or alignment with the radiation. The time scale is characterized through the radiative precision, which depends on the grain size as well, the efficiency of the torque, and also the radiation field. One, we can see that if the magnetic field strength is small and the magnetic susceptibility is small, while the radiation is strong, the time scale, the radiative precision time scale is much shorter than the Lamer procession. So in this case, the radiation fields can align grains without any influence of the magnetic field. Here I show you the time scale as the function of grain size. Dark blue is the Lamer precision time scale, and the red is the radiative precision time scale. So for smaller grain size, grain can be aligned with the magnetic field, but magnetic field, so it can block the magnetic field morphology by rotating the polarization vector by 90 degrees. But for larger grain size, it will be aligned with the radiation field instead of magnetic field. So it can't block the field morphology. So the rotating polarization vector by 90 degrees is wrong in this case. But it's not the end of story. In 2019, we found that the large grain exposed or close to the strong radiation field or higher dust temperature explosive can be spun up to very fast rotation by radiative torques. The induced centrifugal force can exceed the binding force that holds the grain structure together. Therefore, the large grain will spontaneously be disrupted into many smaller species, which we call the radiative torque disruption or RATD mechanism. The disruption efficiency depends on the gas density, radiation strength, and grain porosity. Because the disruption affects on the largest grains, so it could constrain the upper limit of the grain size distribution. So it could affect on the polarization degree at long wavelength also can determine whether PRAD or KRAD, take a place. Then we perform the numerical model to predict the polarization. Here show you at the 850 micron in the y-axis as a function of radiation strength or Green's temperature as in equivalent. We see the monotonic increasing of the polarization degree in case of only rad alignment theory. But when we consider both rad alignment theory and the rad mechanism, the polarization degree first increase and then decrease because of the disruption. The critical value where the rad D occurs depends on the local medium, also depends on the grain structure. More compact grains, harder to be disrupted. Now I show you the case of M51. It's a very beautiful study by Polar in 2020. Basically, M51 is a phase-on galaxy with spiral galaxy with two arms, arm 1 and arm 2 in blue and red respectively, and inter-arm system. The distance to us is about 8.6 megaparsecs. On the table, I show you some very important value for measurement of the synchrotron polarization at 3 and 6 centimeters. Also from the thermal dust polarization with Sophia Hawkless at 154 microns. One interesting here highlight in the red box is the polarization degree in the interarms is higher than in the arm 1 and arm 2. So, and then we try to understand what is there. This here again show you the magnetic field strength in the M51. In the arms are higher than in the interarms. And in the bottom show you the star formation rate. The star formation rate is higher than the arms in arm 1 and arm 2 than the interarms. Therefore, the radiation energy density in the arms is more higher than the interarms. And here it's just the classification of arms and interarm system. And then we calculate the time scale of the BRAD, KRAD, and mechanical torque as a function of grain size on top in arm 1 and arm 2, and in the bottom interarm. Apparently, the BRAD takes place for smaller grain size, and the KRAD and mechanical torque take place for larger grain size as shown before. But when we consider we turn on the rad mechanism, the maximum grain size is determined. The disruption occurs in arms and interarms in both arm and interarms regions, but the disruption affects it more effectively than in the arms than in the interarms. So you can see in here the relative position of the disruption side determined by the vertical line here. And then we calculate the maximum grain size in each pixel in the M51. The blue color code show the large grain size, and the red color code show small grain size. Which we conclude here, the grain size in the interarms, with the blue region here, are larger than interarms region in the red color. Therefore, the polarization degree at far infrared measured by Hawkless in the interarms is higher than in the arms region, which is expected by the rad alignment theory and rad mechanism. So because of the disruption effect, the maximum dust grain wouldn't be very large. Therefore, the BRAD is responsible for the M51. So we come to conclusion. In general, the radiative torque alignment is the leading theory describing grain alignment. The radiative torque disruption or rad mechanism, if occurs, can fragment the larger grain into smaller species, so can define in the upper cluster of grain size distribution, also reducing the polarization degree at longer wavelength. In the case of M51, the rad occurs in both arm and interarms, and is more effective in disrupting large grain in the arms region rather than in the interarms. Therefore, the polarization degree at far infrared interarms consequently lower than the interrupts as is expected by the RAT-A theory and RAT-B mechanism. And finally, the BRAS mechanism is dominant and can be used to trade the magnetic field in the M51 system. So thank you very much for your attention.